Hey everyone, how's it going? This is Dan here. It is a humid day here in New York, a humid Saturday. We just got back from a little run, and we're going to talk about using LLMs for code generation. So, if you're using LLMs for code generation, code auditing, any kind of code-related tasks, probably a couple of problems you run into, whether it's LLMs kind of misunderstanding the logic, kind of just like misunderstanding the instructions, important pieces of the code being left out, or kind of just incorrectly produced, or the context being misunderstood. Usually, the context being misunderstood can be related to the fact that you're asking it to work on like a specific section of code, but it needs knowledge of the whole code base to be able to effectively do what you're asking it. And so there are a lot of unanswered questions about just where do the LMs fail in these steps when trying to get to a output. What are the most common types of code generation errors? Is it syntactical? Is it semantic? And which models fail at which points? Is there a difference? And so it's a lot of trial and error you can get to try to uncover this. There's also a recent paper, which we'll be diving into today, that looks at this exact topic. And so what they did is basically test a bunch of different models, including GPT-4, 3.5, a Salesforce model, something from Meta, and a couple other ones. And they tested on the human eval dataset, which is 164 Python tasks. And so 164 tasks, 6 models. So it's pretty extensive. And in total, there were 558 incorrect code snippets. And they generally categorize these into 2 areas. So semantic errors. So this is logical mistakes, missing conditions, just incorrect logic in the code. It reflects, like I said before, a misunderstanding of the task requirements. And then there's syntactic errors. So specific code errors related to the language, incorrect function arguments, things along those lines. And so in terms of methodology, pretty straightforward. They sent these programming tasks to the model. If there was an error, they got the output. They tested against unit tests that are provided in the eval set as well. If there's an error, they classified it, and then they did a bunch of analyses based on that, which we will take a look at. So some semantic errors include, we touched on this before, but conditional errors, reference errors, just bad code, like unnecessary or like unusable, missing steps, and then also memory errors when you're hitting infinite loops. And so here are the results here. And we could see that, all the LMs share there's a lot of overlap. So incorrect condition is pretty high up on most of the models here. Smaller models like Encoder and CodeGen were more likely to generate meaningless code rather than some of the larger models. Credit that to the larger models are seeing more code and being kind of smarter at this type of stuff. The larger models tended to do more constant value errors, which we can see here, and pretty high up for 3.5 as well. And you can see GPT-4 overall performs the best. Only 7 of the 13 characteristics were even caught. So there's a bunch of 0% for all these other types of semantic errors. So they just didn't even come across those. And so, this could be just contribute to the fact that it's a better model, there's more parameters, more training, and smarter. Something I think that is additionally kind of worth noting here is that for the same, Python task, different LLMs produced buggy code with varying error types. So it wasn't like there was this one Python programming task and all of them produced garbage code for it, or all of the models did this or that. And it points to the fact that different models have very different strengths and require kind of different prompting approaches, different styles, and so a lot of different things to do. Testing obviously is the biggest thing, and if you can find one of these kind of like weak spots through your own testing, if you could figure out what the highest one up on the chart is for your specific model or use case, there's a lot you can do with that. Then you can kind of adjust the prompts to try and solve that specific problem. You could do fine tuning to try and fill in the gaps. You can use different models for specific tasks, although that might be overkill. But again, it points to the fact that different models will have different strengths and require different approaches for prompting, and then also for the other pieces in the stack where you can affect the inputs to get better outputs. So moving on to the syntactic errors, again, this is much more related to the actual code itself. So errors in the if statements, looping errors, functional errors, passing the wrong arguments, things along those lines. And we'll take a look at the results again here. I just got my notes on the left. So we see a pretty similar distribution across all the models. Missing code block or incorrect code block is high for all of the models essentially. And so again, we see GPT-4's errors are more well contained, which is really helpful. It makes it much more predictable. Again, we're seeing a bunch of 0% in many of the categories here. And we can move on to the next. But yeah, the biggest thing I see is super high concentration around missing code block, incorrect code block versus some of the other semantic error types. And, of course, missing code block and incorrect code block are kind of a larger scale, can have kind of sub problems beneath that, of course. And so the next part of the study, which was really interesting, was, okay, errors are one thing, but let's look at how bad these errors are. And so the researchers took all the times that the models produced incorrect code and then looked at two metrics to see just how wrong they were, essentially. So Jacquard similarity and Levenshtein distance. So Jacquard similarity basically looks at all the tokens and then measures the overlap between what is the correct output and what this output from the model is, and it looks at the overlaps of those tokens. Levenshtein distance measures the number of edits needed, whether that's an insertion, deletion, or a substitution to correct the incorrect code snippet. So you want to lower Levenshtein distance, that would indicate fewer. And yeah, so we can take a look at the results here. So on top, we have Jacquard, and the lower, we have the Levenshtein distance. And honestly, it doesn't matter because they both tell the same story. You see big clusters towards the bottom, which basically means when the models produced the incorrect code, it was like very far off. It wasn't just like a little bit, there wasn't just like a lot of overlap with what the correct answer was. There was like very minimal overlap, and it required lots of edits. And so while GPT 3.5 and 4 had the highest overall accuracy, you'll see they had the largest deviations on both of these metrics. And so they usually get it right, but when they get it right, it tends to be quite off. And as we mentioned before, like not every mistake is also equal. And so they broke down just the severity of it, whether it's single line, single hunk, or multi-hunk. Hunk is just like basically a code block. You can see most of it is single or multi-hunk, so not just single line. So these ones require more effort. And so again, this kind of reinforces the fact that when the LLMs did tend to generate incorrect code, it varied or deviated significantly. And then they threw in this really interesting, I think, like additional analysis towards the end, which certainly caught our eye, which was comparing prompt length versus code quality. They called it complexity, and they used prompt length as like a proxy for that. But the actual, what was measured was prompt length. The prompts are pretty short on average. I would say, most of them, the average is 67 to 47% of the prompts include 50 words or less. And we could see basically at smaller prompt lengths, you have a higher success rate. You see bigger clusters on the failure ones as you move up. And for all the passing ones, you see bigger clusters at the bottom here. So prompts fewer than 50 words generally led to better performance. Prompts above 150 significantly increase the likelihood of errors being in the code. The types of the errors in the longer prompts were just like garbage code, so it went on too long and the code just wasn't useful. Meaningless code could be hallucinations. Sometimes it was only comments, which is, I think, interesting. And some was just like wrong logical directions in terms of the mistakes that the LLMs made when they had these larger prompts. And I think this is all very context and use case dependent, but I think it hits on the fact that you just try and keep your prompts short and concise. Too often I will see prompts that are just overly long and kind of repetitive, and I think that can really decrease performance. So again, longer prompts doesn't always mean better prompts. Start with concise and focused ones. Clear and specific task descriptions is always going to be the number one principle here. And I think to kind of clarify, not all long prompts are bad. Long prompts can be great, especially if you're using few-shot prompting. That, of course, will make the prompt longer. But when we're talking about length here, we're really talking about the instructions. So concise instructions. And that is it for today. Thanks, guys.